Let's get started. So welcome to our webinar. My name is Greg Soraki. I'm part of the Habana Labs application engineering team. And I'm here with my partner, Mohit Diopachari, who also will be presenting getting started with Gaudi on Amazon EC2 DL1 instances. So today's session is being recorded and we'll make this available for later viewing. You can use the chat or Q&A feature in Zoom. So we'll field questions real time as we can, or we'll stop and answer. We'll have also Q&A at the end of the presentation to take some dedicated questions. And since we have a group of about 13 people, we can probably take some people off mic or on mic and just interact directly. All right. So what's our objective today? What we'd like to do is really set this workshop as a starting point for those that are interested on using Habana's Synapse AI software stack and Gaudi HPU, Gaudi AI processor. So those of you that are using TensorFlow or PyTorch on CPUs or GPUs or other architectures and want to come over to Habana, this class is for you. So what we'll do today is talk a little bit about the EC2 instance that we have available on AWS. We'll talk about the Gaudi Habana Processing Unit, or HPU. So you'll hear us use this term HPU quite a bit in the presentation and in our code. So that stands for Habana Processing Unit. And the product is called Gaudi. We'll talk about the software stack and our model references and collateral. We'll migrate a PyTorch model to run on Gaudi and show you examples of how simple it is to get your TensorFlow and PyTorch models converted over to run on Gaudi, how to run on 8 cards, and show you a couple examples real time. And then we'll wrap up and take the Q&A. So this is going to be a demonstration today. So we expect this to take about 1 hour. So let's get started. About a year ago, Habana and AWS partnered to launch the DL1 instance. So this is the name of the instance on Amazon EC2. This instance has 8 Gaudi accelerators. So when you rent that instance, you're getting 8 Gaudi HPUs. And we have data that shows this is consistently delivering up to 40% better price performance than current generation GPU-based instances. So we really have a great price performance story. We also provide base Amazon machine images or AMIs, or we can use the AWS provided deep learning AMIs to get started. So once you rent the instance, that AMI either provided by AWS has everything you need, the full software stack, TensorFlow, PyTorch, all the ingredients you need to get started training right away. So you can either use the AWS-based DL AMI or the Habana-based AMIs with TensorFlow and PyTorch Docker images. And Habana keeps updated with the latest releases of both TensorFlow and PyTorch. And that link below gives you some more information on the nature of the instance. What we'll be doing today, all the demos you'll be seeing today on Jupyter Notebook are running directly on the DL1 instance on AWS. So let's get started right away. Let's just jump in and show a model right now. I'm going to bring my screen over. And you'll see here, this is a very simple PyTorch quick start model that we actually took from the PyTorch website. So let's just start running through this. So we're installing Matplotlib and your basic Torch requirements for running a model. The most important part of converting a model and getting it to run on Gaudi is this next instruction right here. So for Habana today, we have our own version of PyTorch. And so this is already running inside the instance. And to import Habana's PyTorch, you run this import command and you set the device to HPU. So we mentioned again, this term HPU is Habana processing unit. And so what this does is make sure that any of our models, when they run on a device, instead of running on a CPU or a GPU, they're running on Habana Gaudi. We run that. And then now the rest of this, that's it. That's all you have to do in this case to run this model and make it run on Gaudi. We'll show one other small example a little bit later. So in this case, we're doing a very simple fashion MNIST data set that we download. We set the data loaders for train and test. And we create this very, very simple model here. So we call this neural network, and we define the forward pass right here. And again, we point to the device. We're using the HPU device, and here's a printout of what the model looks like. We move on down. Again, very simple. We set the loss function on the optimizer. Again, very simple cross entropy loss and stochastic gradient descent model. And then we set the training function. Now, one part I do want to mention here is this. If you remember before, when we imported the Habana PyTorch framework, we called this Habana Torch core, and this function called mark step. Now, the way from a default perspective, when Habana Gaudi executes code, it does it in what we call lazy mode. And what this lazy mode is doing is simply accumulating graphs that don't need to be executed real time. So we have another mode that's called eager mode that executes every graph as it comes in. And that's not necessarily computationally efficient. And so what lazy mode does is compiles graphs together until they all need to be run at one time. And so this significantly improves our compute efficiency. And so to do this, we need to do this mark step command at the end of our backward pass and at the end of the optimizer step. So this is the only other place that you need to add code to your model to ensure that it runs in the most efficient lazy mode we show here. So we define this training function with those two minor additions. We define the test, and then we simply run the model. And that's it. Now, one thing we'll look at here, we have a tool called HLSMI. So those of you that use GPUs, you may see this very similar tool. And what this is simply showing is all 8 Gaudi HPUs. So you can see here 0 through 7. You can see our products. You can see right now this is running on just one Gaudi, so it's running on Gaudi 0, and it's running this Python script, and it's using the full allocated memory, 32 gigs of high bandwidth memory that is on package. And so you can see that it shows you that this is running on Gaudi. And we see in a very traditional run that as we run, the loss continues to go down, our accuracy continues to go up. And we only ran 5 epochs. If we ran more epochs, we would see lower loss and higher accuracy. And that's it. You're done. So this is, if anything, the gist of this webinar is that importing these commands, and the same thing here for TensorFlow, we import the Habana module from the TensorFlow libraries, and we load that Habana module. These are the basic things to do to get your code running on Gaudi. Okay, so what are some of the use cases that we really focus on? So here in Habana, we've really made a focus on these 3 main use cases: object detection and segmentation, image classification, and natural language processing. and these specific use cases. You'll look at we'll show you in a moment our models from our model references, and you'll see that they are all really geared towards these three very specific use cases, which we believe are really, really important in the ecosystem and industry today. So let's talk about our model references. So we have a list of over now 50 models on our GitHub page that are optimized and fully optimized, converted, and performant on Gaudi. These include TensorFlow and PyTorch, covering all those use cases we looked at on the previous page. So let's take a look at our model references, and we'll show you how to run one. So if you go to our GitHub page, this is Habana AI, you will see our model references. And you'll see, again, across those major use cases, you'll see we have a list of models running on TensorFlow and PyTorch, running today on our first gen Gaudi, which is what we have today on the DL1 instance on AWS, and also on our new product, Gaudi 2, which is much higher performance. So you'll see across ResNets, DenseNets, UNet, our natural language NLP models. So our traditional characters, BERT, Transformer, P5. We've implemented DeepSpeed, which is beyond the scope of today's tutorial, but you'll see more information from us on DeepSpeed very soon. And new models here also for inference, audio, and recommender systems. So let's take a look at BERT, for example. In each of our models, we have the fully encapsulated model with all the scripts and all the information to go and run the model. So each one of our models here has a model overview. We talked in this case about what we did to run BERT training and the scripts we've used, what to do BERT fine-tuning, and the setup. This includes the data set, the Docker container, cloning the model references. So in this case, this is just simply cloning the GitHub, which we've already done, and I'll show you this in an example in just a moment. The model requirements, downloading the data set, and then actually running the training. And what you'll see at the bottom of each of our GitHub pages are specific instructions on how to execute the training. So how to properly use the scripts to set up the experiment, or to actually just run the training directly. Let me go through all the details and give you several really good examples of running a very simple example of running on one HPU, which is what we'll demo in just a moment, to scaling up and running on multiple processors. And we'll show you that in here, multi-server training examples. So from one simple card to scaling to multi-node, all this information is provided here in our GitHub page. So let's walk through that example. I'm going to restart the kernel here. So we have an additional notebook here that is our BERT fine-tuning example. So as I showed you a moment ago, we have already cloned the model references to this notebook, and we will start to execute through it, and we'll walk you through it. So we're here in our workshop. We have to set the Python path to make sure that we are seeing all the content in our model references repo. Then we will change into the fine-tuning page for our NLP model. So in our model references, we split between PyTorch and TensorFlow. So today we're doing a PyTorch example using NLP, fine-tuning. In this case, for BERT, we're using the standard Hugging Face version of BERT, and we're in that folder. So once we do that, we have a couple things to install, including transformers, since we're running a Hugging Face model. And then finally, we're here at the model example. So as I showed you on the GitHub page a moment ago, this entire long list that may look a little intimidating is simply what you can copy, and simply copy from our GitHub page and paste it here. And you're able to run the model. And let's kick that off, and we'll walk through a couple of the specific switches here that are important to note. And we'll let this run for a moment. Now, you'll notice a few of these here. So one is Habana Mixed Precision. Moet will go through how Habana implements mixed precision, specifically bfloat 16, in our next example. But we have the ability to define what ops will run on bfloat 16 and what ops will run on FP32. So you can see reference to these two text files that show what ops run on bfloat 16 and what ops run on bfloat 32. We mentioned using lazy mode. So again, this is our example where we are being efficient about how we are managing all the ops before we execute them. You'll see some traditional hyperparameters here in terms of batch size. The dataset name, we're using squad for fine tuning, which is a very traditional thing. Fused atom optimizer. The use HPU command is here. So this is a command you'll see quite a bit in our run commands that inform the script to use the Gaudi HPU. Okay, so now while this is running, and we'll see this is all the traditional Hugging Face runtime, you'll see here that we are actually now running the model. So as this model's running, let's take a step forward and talk a little bit about the Gaudi architecture. So what I'd like to do in these next 2 pages is just talk a little bit about our hardware and our software. So this is a conceptual breakdown of what inside of the Gaudi HPU looks like. So in this case, we have 8 programmable tensor processing cores and a matrix multiplication engine. The key thing here is then are also on-die SRAM and the 4 blocks of high bandwidth memory. These are on package, high bandwidth memory, 32 gigabytes. So this allows you to fit large models directly here on package memory. The other part here that's really unique about Gaudi that no other device has today is our integrated 100 gigabit Ethernet ports. So we have 10 100 gig ports on die on the package. And so instead of having to rely on an external NIC, external host controller for your network access, everything is on package, on chip. And so in the DL1 instance, for example, all 8 Gaudis on that main baseboard are all connected through these 100 gigabit ports. So every Gaudi is connected to every other Gaudi. So that's 7 connections. So that leaves each Gaudi has 3 additional 100 gigabit ports to then connect outside. And this is a significant improvement in efficiency and cost reduction on system design. When we look at the software stack, we call our software stack Synapse AI software suite. And this is a generalized software suite that we use for training and inference across our entire product line. So today we're talking about Gaudi. I did mention we have our follow-on product, Gaudi 2, and we have announced Greco, which is our new product specifically designed for inference. And all these products run independently on this Synapse AI software stack. So from a usage perspective, You don't have to worry about writing specific code or dealing with how, if you're running on Gaudi or Gaudi 2 or Greco, running inference or training, the Synapse AI software stack will handle all those configurations. We're optimized for deep learning training and inference with minimal code changes to the PyTorch and TensorFlow models. And you'll just see from the example we showed you just a minute ago, the code changes are very minimal to take your PyTorch and TensorFlow models and convert them over to running on Synapse AI software stack. So one of the key things here is our framework integration layer or bridge. So we have a bridge between PyTorch and TensorFlow, and that converts all of our code to run on our graph compiler. And so our graph compiler is optimizing the ops and commands coming from the frameworks down to run directly onto our hardware. We additionally have what we call HCL or Habana communication libraries. So this is used for our scale up and scale out communication. So communication between cards and communication between nodes. In this case, we have our own nickel-based library. We call it HCCL or HICL. That has the same APIs and calls as the nickel APIs that you see in other places. We have our own kernels that run with our graph compiler. And we have the ability to provide you to run and create your own kernels as well. Supported by all this is our developer site, our GitHub, and our developer forum. And I'll show you a few of those at the very end. All right, so let's take a look back here at our BERT fine tuning. Let's see where we completed. So our training is completed. And in this case, we trained at about 100 samples per second. Our previous workshops, we were doing this about 88 samples per second. We're now up to 100. So a great example. And again, the key point here is that all you had to do as a user is come back here and pull the data and run this command. And this is basically what we ran in our example here. All right. So let's summarize the key things we need here for TensorFlow and PyTorch. Again, as we said early on, the rest of your TensorFlow model is your standard TensorFlow pieces. The key thing here is pulling in the Habana module from the TensorFlow that we've upstreamed. So in this case, the only command you have is load Habana module. So for TensorFlow, it's 2 lines of code. And then with PyTorch, again, we talked about importing the Habana frameworks. So the Habana fork of PyTorch, and we just call that Habana Torch Core. And we talked about those 2 mark steps that you need to do after loss and optimizers to trigger that lazy mode execution of all those compiled ops. And then finally, in the main, we make sure that we're targeting the device to HPU so that when we are actually running the model and executing the training or executing the test pass, that all of that work is being pushed to the HPU, pushed to Gaudi. And again, the details of this and some very simple examples also exist in our collateral and documentation. Okay, so I'm going to hand this off now to Moet. I'm going to stop sharing. Moet, you can pick this up and show us a more detailed ResNet 152 example.
Sure, Greg. Thank you so much. I'll start by sharing my screen. Okay, so let me know when you can see the screen.
See it?
All right, perfect. So yeah, just like Greg mentioned, we're going to look at another PyTorch training example on Gaudi. This is a ResNet 152 classification vision model. And we're going to see how to train it on 1 Gaudi instance first, like one HPU, and then after that on multiple HPUs, which is like 8 HPUs in this example. So let's start. The first things first, we need matplotlib just to preview our dataset. So let's install that. And then we're going to download and prepare this CFAR10 dataset. CFAR10 is a very popular dataset, a very simple dataset, contains around 60,000 color images. So we're going to download that and preview that. We need some basic imports for that we're doing here. And this is the how you download the dataset. You'll set the train loader. This is prepackaged as part of Torch utils. So let's do that. All right, let's preview it. Let's see how it looks like. All right, here's a bunch of images with the names and labels associated with those. So we're going to now deep dive into how do we set up our Gaudi instance. So first of all, you need to set up the environment variables for this lab. We're pointing our Python path to the model references, which is like the model garden. And we're pointing it to this specific folder where we're going to load the model from and run the script from. So let's set that. We're going to cd into that directory. So on the GitHub page, if you want to go to check out the script, you can go here, model references, PyTorch, computer vision, classification, and torch vision. So again, I'm going to highlight the steps required for migrating this model to Habana Gaudi HPU. First things first, you need the HT core Habana torch library. That's the first import. So we do it like this, set a single line. And we need to let the torch framework know that we want to run this model on our HPU device, the Gaudi HPU device. And how we do that is through this line. Usually you would target some other device here, but this is how we target HPU. Just put the name HPU in torch device, and that's your device handle now. And later on, in lazy mode, we'll need this line here right after loss.backward and optimizer.step, like Greg mentioned earlier. So what this does is it's gonna let the Habana bridge to accumulate all these ops in a graph, and then you trigger the execution of that graph only when needed, only when a tensor value is required by user. Until then, all these ops get accumulated, and that gives the graph compiler an opportunity to optimize the graph, the device execution for these ops. So we'll look at that, how to do that in the code next. So here we're going to import some libraries and define the argument parser for our code. And so I'll just highlight again the key changes required. Just import the Habana torch library here and target the HPU device. The rest of the stuff is pretty much standard. You have a standard script with a standard argument parser. And now in this main training function, we're just going to need to uncomment the mark step code at the right places. This is the loss.backward. And this is optimizer.step right here. Let's save that. So just two places I need to add this mark step. And the rest of the training loop is pretty much the same, just how you would do it on any other device. So let's get that going. Let's see, okay. So there's some environment variables that are necessary before we run our program. So that will be done here. More information on this can be looked up in Habana Gaudi documentation online. And we're going to parse these arguments. We're going to send these arguments. Note again, we're using the HMP flag here, which means Habana mixed precision. We along with this flag, we are specifying which ops we need to be able to run in the BF16 mode, which is and the other ops which we want to run in full FP32 mode. We specify that here in this text file. Now, why this is important, why HMP is important, is because it allows you to run mixed precision training on HPU. As you can see, we didn't do any extensive modifications to our script. It's a very basic, simple step, and that allows us to run in mixed precision. It gives you this added benefit of good performance with less usage of memory, more speed, at the very little cost of accuracy. So it's a very good trade-off, and definitely recommended. So that is where Habana specializes in. So let's look at that now. Let's run this. We've set up the arc parser. We've looked at how to do HMP. So this is where we are going to do the actual HMP conversion. We're going to convert all the ops that are needed in the BF16 mode. And now this is the next step where we're going to load the data into our model and run the actual training. So let's do that. As you can see, it's creating the model. This model is the PyTorch ResNet 152, comes from the Torch Vision library. And then this training will begin. All right, as you can see, the model is training in HP with the HMP enabled, and that's going to run. So this is going to run a long time, so we'll stop it here before we move on to the next step, which is distributed training. So let's do that. So here in the next step, now we need to restart the kernel because we're going to do it again. Okay. Now here in this next step, we need only 3 things to migrate a single model, so like a single HPU model run onto an 8 HPU model run. First of all, you'll need to initialize the HCCL. So you're telling the distributed libraries about the backend, which is the HCCL Habana communication library. And we're specifying the world size here. So in our case, our world size will be 8 HPUs. This is one of the first changes that you'll do in the main script. Second thing to note is we're going to use a distributed sampler on the data set. We are not using a simple data sampler here because we need to send it across to 8 devices. And also our model is going to be called with this distributed data parallel model wrapper. This is a special Torch wrapper that helps you to run this model in a distributed fashion across multiple devices. So let's look at that now. We're starting from afresh. We restarted the kernel. So we need to set the environment variables again, just like how we did for the single run. And we CD into that library. So before we proceed, the original Model Garden script, it uses a basic, it allows you to run your own data set, like load your own data set. But for this example, we're going to use the CFAR data set. So for that, I have a patch ready with me. We're just going to quickly look at what that patch does before we apply it to the script. So in the original script, the training script, we have this, like I said, custom image folder, which you can specify whatever data set you want. But in this example, we're using a CFAR10 dataset. So this patch is going to replace this image folder and apply the CFAR10 dataset here. Same thing for the test and validation datasets. We replace the original with CFAR10. And we also turn off evaluation. We're not interested in looking at the evaluation and accuracy results right now. So just for that purpose, we're going to do this. Let's apply this patch. After applying this patch, you'll note this is the main training script here inside model references. Let's quickly look at that, how the modification went through. All right, I think we need to refresh the file browser. Okay, let's go back to this training script. Now that this patch has been applied, this is the final command that we're going to run. We're going to use the MPI run library to distribute our training script across the 8 devices. The main training program is pretty much like this. This is our training code. Like this is the training arguments that we send. But when you want to distribute it across 8 devices, here are some additional arguments that you need. Using the MPI run library, you need to specify the master address, master port, and all that is being done here in this shell script that I have packaged. So let's do that here. As you can see, there's multiple initializations happening. You can see there's multiple init happening and each rank is being specified. So we are targeting 8 devices. There's 0 through 8 ranks here. Okay, so I see that some processes occupying our server socket. So we can really quickly look at that here. So we'll kill all the processes that are occupying our socket here. In this case, we were running a single node. So that's the process that's occupying our socket. So we need to kill that fully. All right, let's try this again. Okay, this time it proceeded. We've created the model, started training. We're going to see the same message being printed like 8 times, especially the warnings, because we are running it on 8 separate HPUs. Meanwhile, we can start to summarize what we learned here. We'll wait for this training to proceed. In the meantime, so this is what we did. We downloaded and previewed the CFAR10 dataset. We learned all the steps needed for migrating the model to Habana HPU, which was specifically importing the HD core library and targeting the HPU device. Then we got to know how to use HMP, which is the Habana Mixed Precision. The added benefit being more speed in training and less memory usage at the very little cost of accuracy. Also, we trained the ResNet 152 model on a single HPU and then reconfigured the training scripts and ran it on 8 HPUs. As you can see, we got our first few steps here, and we are running this at a nice 40 images per second. So yeah, any questions, you're welcome to ask us. I'll hand over to Greg. Thank you, Greg. Take over, please.
Okay, coming off mute. So let's go back to our presentation. And we'll wrap up and have some Q&A. Moment. So, thank you, Mohit. As Mohit said, we walked you through the main steps to get your model migrated over to run mixed precision and to run on all 8 cards on a DL1 instance. I do want to raise a few other areas of support and capability here. So I want to bring a few things to everyone's attention. So one is we already looked at our model references. So a great place to start for you to just use our existing models to run them yourself or to modify them as needed. Our documentation, so docs.habana.ai. This is the place to go to get the detailed information to run our products. And I'll point you to PyTorch. So here we have our migration and getting started guide and our user guide. So if you need those steps detailed, as we've been talking about, and where they fall into a simple model, you can come here and take a look at this offline. And then our developer site, so developer.habana.ai, has a great deal of resources here in terms of how to get started on a DL1 instance, our performance data, software setup, if you need to do that, and additional videos on how to get started. So some great resources here to follow. And then finally, our developer forum, which in this case is open here for people like you in the public that want to ask Habana any specific questions. So outside of today's Q&A that we'll have here for the next few minutes, if you want to come back and engage with us again, come here to the forum and post a question. And you'll be talking to myself, Moet, and many others inside the company answering your questions. And again, from AWS, we have the marketplace. So within the marketplace, as you stand up an image, you can use our base AMI images that we provide, as well as our Docker images for PyTorch and TensorFlow. And for those that are looking to do orchestration and other areas, we have a gallery here for Habana's, or for AWS's Elastic Container Registry. Okay. So we'll go to Q&A. And I'm already seeing a few questions. So first one from Boris. So my team uses a modified version of PyTorch. How hard would it be to patch Habana specific changes into a customized PyTorch? I've been asking some folks, and I don't know the answer to the question. Moet, I don't know if you want to take a stab, or Ken, but we can take this one offline. So Boris, if you put your email address here, we can take that offline and give you a better answer.
Yeah. To provide better answer, we'll need to understand what kind of modified version of PyTorch you're using. And you can take a look at the version itself we have on the support metrics. We have the version of PyTorch that we support. And currently, the PyTorch that we provide is patched also. So we need more details to provide better answer.
Okay. Then the next question was a question about how do I tune the learning rate and batch size to take advantage of the huge amount of memory available on 8x HPU setup. Right. So in general, let's go back to one of our models here. And we can use this as an example. So I think the question is related to how do I maximize learning rate and batch size? Right. So Moet, you want to take this one in terms of what's some. I'll point to some of our BKMs in a moment, but
Sure.
Do you want to try answering this one?
Yeah, I'll tell a few examples in my case. Like for some of the examples that we enabled, which we migrated to Habana Gaudi, we went into the actual paper of the model and how they did the fine tuning there, like how they scaled it to run on multiple GPUs for say instance. And from there, we got an idea on what kind of learning rate would be beneficial. In terms of the memory usage, we are aware of how much memory each HPU has. We have a good feeling for that. So we go by batch size. Like we try to it's more like trial and error thing, but we try to maximize the batch size until we go out of memory, and then from there we try to scale it down to see which batch size works best at a good performance rate. So that's how we initially did all our enablement. So yeah, I would recommend looking into the research paper for the model itself. There may be some clues there. Other than that, like I said, for the batch size, you can try going all the way up to whenever your model goes out of memory on the device, and then start scaling down from there. Usually, we try to maximize the batch size, so that gives better performance. I hope that gives you a general direction.
Okay, and then there's a question on support for Onyx runtime. So Ken, we have Ken here from the product team. So Ken, would you like to answer that one? Anyway, the short answer is at this point, we do not support Onyx runtime. So we're focusing on just native PyTorch, really focusing on PyTorch inference. And since I have my screen sharing, I'll point to our inference section in our collateral. And you can see here the specific instructions on how to run inference using native PyTorch. So that's been our focus right now. But as we always look at customer needs and ecosystem advancements, we can evaluate looking at some of those other things. But right now, Onyx runtime is not in our immediate roadmap. Okay, and then to the previous question, I'll also make sure people see we have our model performance optimization guide. So as we collect key things for us that we learn in terms of how we work with other customers and other people and our own internal investigations, we always add a bunch of information here to our optimization guide.
There was a question from Evelyn, which I answered on text, but just to be clear, the question was around pre-training on Gaudi and then fine-tuning on CPU or GPU, and maybe vice versa. So as I answered, like you can pre-train on Gaudi and then fine-tune CPU, GPU. You can pre-train on GPU, CPU, and then fine-tune on Gaudi. It should work. If it doesn't work, like it says here from my experience, it doesn't work. So if it doesn't work, that's an issue. Feel free to file a ticket on our forum, and our support team can help. It should work. We also have a recent blog post around that.
Yeah, Evelyn, please reach out to us. We can go work with you independently offline on that one. As Ken said, if you can either go through our forum, or if you have service desk access, please reach out to us. Okay, so we'll stay. Thank you. We'll stay for just another couple of moments. And again, if we run out of time and people want to or have questions to come back later, or you go back and review the collateral, please come in here to our developer forum, forum.habana.ai, and you can jump in here and post a question, and we will respond. Okay. So I think we've exhausted. I'd like to thank everyone for coming and sitting with us for the hour. Hopefully you found that effective. We enjoyed presenting it to you. So thank you, Moet, for presenting, and Ken for being here and helping out. So hope to see you all very soon in another webinar or maybe at another event out the ecosystem. But again, please reach out over the forum and we'll be happy to engage with you further. So thank you all, and we'll end the meeting. Thank you.